Perhaps we can wait for 2 or 3 minutes as we're not complete, and then we start with the third part of the applied micro. Okay, so let's start now. So I will share my screen. So as you know, last week we started with the now you can see my screen. Last week we started with the introduction for what's the problem that we have in terms of the causal inference or the identification strategy that we need to have in applied microeconometrics. What are the consequences of not properly identifying the causal relationship? And based on that, we provided some solutions using either experimental methods like the RCTs or quasi experiments like the difference in difference PSM or the IV. And based on that, after this general introduction, we had last week the first session on the PSM, and today we're going to see the second tool or the second approach, which is the panel models. And as we'll see today, we're going to have two main parts as usual. The first part will be more theoretical, and the second part will be more applied. So for the panel models, I will proceed as follows. So I will start with the general introduction, then present the fixed effects, the random effects, how these two approaches they can help us address part of the or the problem of the identification that we talked about last week, and then how to choose between them, and then we're going to see a data application, a general one, and then a more focused one using the labor force survey, the Egyptian labor market panel survey that is available on the website of the Economic Research Forum. So to start with, clearly, as you know, we have different types of data sets. So if the number of observation, if the number of individuals is just one individual, so one country, one household, and the time dimension is greater than one, so in this case we have a time series analysis with all the time series techniques ranging from the VAR model, the VEC or the error correction model, the ARDL model, and so on. And those are, we do have at ERF one of the training workshops on the applied time series econometrics. So we do not cover it in this course. The second one, which is the cross-section, or the second type of data, which is cross-section, and in this case we have just one point at a time and more than one individual. Then if we have more than 1 year and more than one individual, so in this case, T is greater than one, N is greater than one, but the time then dimension is lower than the individual dimension, then in this case, we have the panel analysis. And the panel analysis, what we're going to see today in this workshop. And I remind you that one of the important conditions that must be satisfied is that the number of individuals is greater than the number of years. And this is, for instance, the case of labor force surveys, income, expenditure, and consumption survey, firm level surveys, because in general, we are talking about at least 1,000 individuals, household, firm, or individuals, as I said. And we have 2 or 3 or even 10 rounds, which means in this case that the time dimension is lower than the individual dimension. And when it's the case, we can use the panel analysis that we're going to see today. But if we have more than an individual and more than a year, so in this case, time is greater than one, n is greater than one, but the time dimension is greater than the individual dimension, which means that we have for each individual, let's say we have 20 countries or 30 countries, and we have for each country 60 years. In this case, the number of years is greater than the number of countries. And in this case, the time series properties of the countries matter. And that's why we have to apply the time series cross-section techniques or the time series panel techniques. And it's a very large and growing literature that was initiated by, among others, Hashim Pesaran, with the pooled mean group techniques, the mean group techniques, and the cross-section dependence, and so on. And again, it's also another type of panel econometrics that will not cover because it requires a totally different set of assumptions. So that's why what we're going to focus on is the this third point where the individual dimension is greater than one, the time dimension is greater than one, but the time dimension is lower than the individual dimensions. Any
Excuse me,
questions
Shahir.
before I proceed?
Excuse me, Shahir, can you hear me?
Yes.
Okay, so what if time and number of observations are the same? What if they're equal?
Well, it will really depend on the length itself of what we have. So for instance, if we're talking about a long time series, in this case, it's preferable to use the time series technique, especially or not specially. What's the reason behind? Because probably if we have a long time series, let's say 25 years for each individual or 30 years for each individual, then in this case, we might have some non-stationarity. And if we have some non-stationarity, this will have I mean the main implication of that is that we can have a spurious regression and we have to correct for this. So the longer the time span, perhaps the more probable it's better to use the time series technique. But if we're talking about 2 to 10 years, there is no risk for stationarity because at least two things. First, because time dimension is not very long. And second, because in most of the cases, the surveys are not annual. They are, let's say, every 2 to 3 years, 5 years, even in some cases, 10 years. So it's very rare to have a problem of non-stationarity in such a structure of data. Other questions? Okay. So the basic structure of the panel data, as you might know, we have different individuals, and for each individual, we observe all the characteristics for the same individuals over time or over different surveys. And this is very important to bear in mind. Why? Because in several countries in the MENA region, in some data sets that are collected by different statistical institutes or the World Bank Enterprise Survey that collects the Enterprise Survey. I mean, the World Bank that collects the Enterprise Survey, that's called the World Bank Enterprise Survey. In several cases, we have firm level data or household data where we collect, let's say, in round one, 1,000 individuals, okay? In round two, over the 1,000 individuals that we have in round one, we can follow up with, let's say, 300 individuals only. And then we're going to have 700 that do not exist in the first data set, which means in this case that the panel dimension of my data set will apply only to 300 individuals that are observed in both periods or in both rounds of the surveys. If I combine all the individuals together in one data set, which means that I'm going to have the individuals that exist in round one and not in round two, the individuals that exist in round two and not in round one, and those that exist in the two rounds, if I combine them together, we're going to have a pooled data set. And if we work with a pooled data set, we cannot use the panel techniques because we do not follow the same individuals. And this is very important when we use, especially the World Bank Enterprise Survey, because in the World Bank Enterprise Survey, we do have a lot of samples that exist in one year and that do not exist in other years. Okay? Uh, so for the basic structure of a real panel, it's the case where we observe in all the surveys the same individuals. And that's the most important criteria that we have to bear in mind. And we're going to understand later why this is important and why we have to have this in our data. Okay? So to just a very quick definition or introduction of what we're going to see. In general, the panel data models, their main objective is to account for correlation between observable variables and unobservable variables. In the sense that if I have, let's say, if I do observe in this training workshop, we are around 20 participants. Okay, I can have some observables in the sense that I can ask, for instance, Muhammad about his age, his income, his gender, his location, and so on. I can ask Hassan the same questions, and I can ask Nadine the same questions, and so on. So in this case, I do have some observables that I can observe over time on the one hand, but at the same time, I can have some variables that are not observable and that are related to some unobservables at the individual level, in the sense that some intrinsic characteristics that Hassan has, his enthusiasm, his intelligence, his emotions, and all this is unobservables. The same thing applies to Muhammad. I cannot observe everything, and Seda, and so on. So if I have to control for those unobservables, I must make sure that I'm observing the same individuals over time to make sure that these characteristics are controlled for. And I will get back to this later. So in general, the heterogeneity that you observe between observables and non-observables can be caused by multiple factors, or this heterogeneity that you observe at the data level can be due to different reasons. First, a problem of simultaneity, in the sense that the independent variables are correlated with the dependent variable, or a measurement error, in the sense that the dependent variables can be correlated with the error term. And we talked about this in the orthogonality assumption last week. And in this case, there is the coefficients will be biased. So in this case, in order to control for this heterogeneity that we have in the data, and in order to control for unobservables, we need to use the panel data models. Okay? So the basic definition of that is that panel data regression models, they are based on panel data, where observation are for the same individuals that are observed over time. Okay? And we can have two types of panel. The balanced panel, where we observe for all individuals data in all the surveys, or in different years. That's on the one hand. And we can have an unbalanced panel in the case where we do observe data for most of the individuals in most of the years, but not necessarily for all years. In the sense that I can have, for instance, data for Lebanon between 2000 and 2020, but for Egypt, data starts in 1990, for instance. And in this case, it will be an unbalanced panel. Okay? So the balanced panel has the same number of time observation for each cross-sectional unit. And this might not the case for all our variables, because we will see later that in some cases I can have some missings in the data set. And then clearly, among the main advantages of the panel data is that when we compare it to cross-section data, is that it increases my sample size, because I don't have only an individual dimension, but I have also a time dimension for all individuals, which means that the sample size will increase. And if it increases, then it will increase the robustness of the results. Second, I can study the evolution of some variables over time in order to see how the behavior of individuals, for instance, changes over time. And third, we can also control for time invariant variables. And I will come back to this later, in the sense that anything that is time invariant or constant over time, it can be took into consideration. Okay? So those are the advantages of using a panel data model. And these graphs summarize the different possibilities that we do have. So in the first graph, which is this one, and this one is the most familiar for you, because it's the case where we have the same slope and the same intercept for different individuals in the data set. Okay? And in this case, here we are running the regression using simple OLS, where we assume that I have just one intercept, which is alpha, and the same slope for all individuals, which is beta x. Okay? So here the slope is alpha. The intercept is alpha, the slope is beta, and it's the same for everyone. And that's the classical case of OLS. So here we have just one slope, constant intercept for everyone. The second possibility is the uh, the case where we have the same slope but different intercepts. So here I have, let's say, an intercept for Lebanon, an intercept for Tunisia, an intercept for Morocco, an intercept for Egypt. But all the countries, as you can see, they have the same slope. So here we have constant slopes and different intercepts. And that's what we call the fixed effect model. And we're going to understand this furthermore when we talk about fixed effects model. But for now, I just want to contrast the two cases that we have, where here I have constant slopes and a constant intercept, and here we have constant slopes but different intercepts. And that's what we call the fixed effects model. Okay? The other two cases are when we have different slopes but the same intercept, and this is very unlikely to occur in the sense that it's very difficult to assume that all individuals will depart from the same intercept and that they have different slopes, right? Finally, the last case is where we have different intercepts and different slopes, and in this case, as if we're running a regression for each country on its own. So I will run a regression for Morocco, I will run a regression for Egypt, and I will run a regression for Sudan. Okay? So in this case, those are the different possibilities that we can have of the intercepts and slopes from the classical case where we have a constant slope and a constant intercept for all individuals, and that's the classical OLS, where we have constant slope but varying intercepts, and that's the fixed effects model. Different slopes and different intercepts, here we have as if we're running different regressions for each individual. And finally, the case where we have different slopes but the same intercept, which is not very likely to happen. And this what you can see here in the in this graph. Okay. Any questions? Okay. Clearly, if I'm observing different individuals over time, as I said, if I observe Muhammad or Nadine over time, there is part of their personality that I cannot observe because I can ask them for their wage, for their education, for the background of their parents, for their marital status, for their job, for everything that I can measure and observe. But there are some things that cannot be properly measured or properly included in the model. That's why this can lead to some unobserved heterogeneity, as if I should have included some variables, but I did not include them. And if I do not include them, this can lead to an omitted variable bias in the sense that I do not include an important variable. And if I do not include an important variable, this will lead to an omitted variable bias, which means that the model can be misspecified. And this can include the enthusiasm, the intelligence, the emotional intelligence, the sociability, a lot of things that can characterize each individual and cannot be explicitly or properly measured. That's why it can lead to an heterogeneity that is unobserved because I cannot observe it. And if these variables, they affect my outcome variable, this means that I will have biased results of my estimates in the sense that perhaps the enthusiasm of Seda can affect its wage because she's enthusiastic and she wants to she's working on different papers, and this increases her performance, for instance. Okay. And in this case, the unobserved heterogeneity can be interpreted as an omitted variable bias. So that's why such an observed heterogeneity can affect the results of my estimation, and that's why it's important to take all those unobservables into consideration. Okay? Any questions on the unobserved heterogeneity? Okay.
Thank you, Mr. Dr.
Yes.
Shahir. What about the observed heterogeneity?
So for the observable, it's a bit easier because I can measure the variables. For instance, I can ask you for your age in a survey collected in 2010 and in the second round in 2015. I can ask you for your wage in 2010 and in 2015. I can ask you for your marital status in 2010 and in 2015. So all the variables that I can observe and measure, it's not a problem because I can include them in the model. The problem comes from the fact that there are some variables that can affect my outcome variable that cannot be observed and that can lead to this heterogeneity. That's why it can my model will suffer from an unobserved heterogeneity.
Okay, we can say that all introduced variables, if we have heterogeneity, we can say that all introduced variables can be an observed, constitute an observed heterogeneity.
Constitute an observed, not unobserved,
Observed,
observed.
observed, yes.
Yes, yes.
Okay, thank you.
Okay,
One more thing on this, Shahir, please.
yes.
Why is heterogeneity a bad thing in regression in general? I mean, obviously we expect that there will be differences across units over time, right? So why should it affect and bias our results in this case?
It's not the heterogeneity per se, it's the fact that it's unobserved. Because if in general, heterogeneity is good, because if I have a variability in my data set, then in this case, this means that I can get some results, because if my sample includes
Mm,
identical individuals, then I cannot get
mm.
an estimate. So the problem is not the heterogeneity, the problem is that this heterogeneity is unobserved. And that's why if it's unobserved, it's similar to the case where I have an important variable that should have been introduced in my model, but I didn't introduce it because I can't measure it. And if this variable is not introduced in the model, it leads to an observed heterogeneity, which means that as long as it's not introduced, there is an omitted variable bias.
So we care about unobserved heterogeneity.
Exactly. Because
Okay, thank
observed can be introduced.
you. Thank you.
Okay. Clearly, despite those advantages of the panel models, they suffer also from some problems, in the sense that the most serious problem clearly is the problem of attrition, in the sense that if I run a survey in 2020 in order to examine the effect of the pandemic on Egyptian firms, for instance, and then I decided to run a second survey in 2024 for the same firms in order to see how they behaved between these 2 points in time. So if I run the regression in 2024, perhaps some firms they refuse to participate in the survey. Some firms they do not exist anymore. Some firms were based in an apartment, and this apartment became a residential apartment, not a commercial one. Which means that in this case we can have a problem of attrition. And in this case, why the attrition? It's due to the fact that some individuals might drop out over time. So in this case, I will not be able to follow the same individuals over time. Okay? Or simply, if I'm running an individual survey, the participants might refuse to participate. I mean, or to answer some questions. So that's why we can have a problem of attrition. Okay, and this clearly affects the panel structure, because this means that I will not be able to observe the same individuals over time. Okay, so bearing this in mind with the data structure, the idea of the unobserved heterogeneity, and the idea of what to take into why we have to take this unobserved heterogeneity into consideration, and the different possibilities that we have, we'll start first with the fixed effects model and then move to the random effects. Okay. So the first model, which is the fixed effects model, and in general, It's widely used in macro papers and micro papers for different reasons, and we're going to explain that. So for the fixed effect model, that's the structure of the data. I remind you that from now on, our variables will have two indices, I and T. I for the individual and T for time. Okay? We have the vector of explanatory variable that changed by individual and time as well. We have the error term that changes by I and T. And here we're going to introduce, here we have our initial intercept, which is alpha. And then we have here two effects, an individual effect and a time effect. What does the mu and the lambda mean? I remind you that the other three parameters that we have here and that are in blue, they are the classical terms that we have in a normal OLS regression. What is different is those in red, which is the mu and the lambda. Okay? Clearly, in a classical OLS model, these three terms are combined together under an error term that we call U, and that's what we have here. So in a classical OLS model, the error term will be U, but in reality, it can include three components, the mu I, the lambda T, and a nu IT, which is this last one. So what does mu I represent? Here, the mu I represents the unobserved cross-sectional individual effect for n cross-sections, in the sense that as if I'm introducing a dummy variable for each individual of you. So let's imagine that we have a sample where we have in the sample Rashida, Aya, Evran, and Hassan. Okay? So what I will do is that I will include a dummy variable that takes the value of 1 if the individual is Rashida and 0 otherwise. And then I will introduce a second dummy variable if the individual is Hassan and 0 otherwise. Then I will introduce a third dummy variable that takes the value of 1 if the individual is Zahra and 0 otherwise, and so on. So here I'm introducing a fixed effect for each individual, right? And I will explain why later. This one is the year fixed effect, in the sense that if I have 3 years, let's say I have 3 rounds for the survey, 2012, 2016, and 2018. So I have 3 rounds of the survey. So I will introduce a dummy variable that takes the value of 1 if the year is 2012 and 0 otherwise. Another dummy variable if the if the year is 2016 and 0 otherwise, and so on. Okay? So these two dummies that we do have here, they control for the unobservable cross-section, mu, and the unobservable time series effects, which is measured by the lambda t. So here, by doing this, I'm controlling for anything that is unobservable. For instance, the dummy variable for Zahra measures all the characteristics that I cannot measure for Zahra and that are time invariant. So over time, Zahra has some characteristics that did not evolve over time, and they are measured by her dummy variable. The same if I include a dummy variable for Aya. So those characteristics, they will be included. Anything that is unobservable for Aya will be included in her dummy variable, and so on. So if I have 15 individuals, right, in my data set, how many dummy variables should be included from your perspective? What do you think?
The
Is it
same number.
14?
Yes, so to avoid dummy variable trap, we have to include in this case we include in general n minus 1, so it will be 14. And again, if we have 3 years, I will introduce 2 dummy variables for each year. So now the issue is the fact that we're going to have a fixed effect model or a random effect model will be attributed to the way we introduce these two terms, okay? How they are treated, in other words. So most of our analysis now is going to focus on these two terms in order to see when they are introduced in which part we can have a fixed effect model or a random effect model, okay? So let's start with this this econometric specification, okay, where we have yit that is equal to alpha beta xit theta ti gamma tit and theta t, okay, and the error term. So our consistent we have a first set of assumptions that we have already seen, so it will be quick. So here the most important assumptions that have to be or the conditions that have to be satisfied: first, linearity with respect to the independent variable xt and t and the error term; exogeneity, which means that the expected value of the error term is equal to 0, and that we have orthogonality in the sense that the error term are not correlated with the explanatory variables xit that we have here. And the error term also is independent and identically distributed, and they have the same variance, which means that the error term is homoscedastic. And the error terms are not correlated to each other, which means that we don't have an autocorrelation. Then the independent variable x is non-stochastic because it's predetermined, and we all know that from the basic econometrics. And finally, that we don't have an exact multicollinearity among the independent variables, in the sense that I cannot introduce, for instance, in the same regression, a dummy variable that takes the value of 1 if the individual is male, and at the same time introduce another variable that takes the value of 1 if the individual is female, right? So that's why we can, because this will lead to a perfect multicollinearity. And if we have a perfect multicollinearity, this means that the matrix will not be inverted. And if it's not inverted, then we cannot get the estimates. So we must have we can have, I mean, some collinearity. It can affect just the efficiency of my results, but not a perfect multicollinearity between the independent variables, okay? So those are the basic assumptions that we have for OLS and that you have seen. But the idea, as I said, is how to treat this error term. So the idea of the fixed effects and the random effect, I will briefly introduce the main difference between them and then present each one of them with some more details. So as I said, I remind you that my data structure here includes both individuals, an individual dimension and a time dimension. So if you remember, we had in the first slide, this model, right? So basically, what we do in a in a fixed effects model is that we take this individual effect and we combine it with the intercept, okay? So in other words, I'm going to have alpha plus mu I that will represent the new intercept, okay? And in this case, Is alpha constant or not? What do you think? Is alpha on its own constant or not?
No, it will change with
No,
every
alpha.
observation.
Alpha per se, alpha on its own.
Yes, it's constant.
Yes, we can say that it's constant.
Alpha per se is constant, exactly. And mu I is constant or not?
No, it will change with the cross sections.
So it will change with the cross section because each individual will have a different dummy. Which means in this case, if I combine the two terms together, the intercept will be varying by individual. And that's why in this case we have to have an intercept for each individual because the intercept will be decomposed in two parts. Part that is constant and part that is not constant. A part that is constant, which is alpha, and a part that is not constant, which is mu, because it changes by individual. And that's why if we look back to the graph that we had that we have seen in the beginning, here, as you can see, I have the same slope for everyone, so the same beta, but what is constant is, sorry, I have the same slope, but what is changing from an individual to the other is its intercept. So I have here the first intercept, the second intercept. So each individual has an intercept on his or her own. And that's why if we introduce this fixed effects model, in this case, what we're basically doing is that we are combining here the alpha with the UI, which means that here these two terms, I'm combining the individual effects with the initial intercept that I have. Okay? For the random effects, I do not do that because I will going to have the same intercept for everyone, the same slope. So it's basically an OLS, but I will combine this individual effect with the error term. Okay? So in this case, this UI or this individual effect that is observed over time, in the fixed effects model, it's part of the intercept, but in the random effects model, it's part of it's part of the error term. Okay, so UI is either a fixed effect specific to each individual, as I said, and in this case, because it's part of the characteristics of the individual. And the error term here is nu I, t, and we can clearly see that this error term does not include the individual effect, which means in this case that, and I will relate this to the orthogonality, if I do not include the UI here, so the error term just includes the new IT. So if the new IT, which is the small v, is, satisfies the normal conditions that we have heteroscedasticity, that the expected value of the error term is 0, in this case, as long as the individual effect is not part of the error term, this means that there is no omitted variable bias. And if there is no omitted variable bias, this means that the error term might not be correlated to the explanatory variables, and therefore the problem that we had with the unobserved characteristics is resolved. Why? Because those unobserved effects at the individual level are are introduced as part of the intercept. Okay, so that's the first point. So in this case, this error term has a constant variance and it does not change with the individual. And the UI in this case, that is part of the intercept, even if it is correlated with the explanatory variable, it does not lead to a bias. Why from your perspective? I will ask once again the question, why, if the UI in the fixed effects model, once it is introduced with the intercept, even if it is correlated with XIT, why it does not create a bias in our estimation? What do you think? Any insights, any inputs?
I think that because it will change from an individual to another.
Yes, but why it does not create a problem of I mean a bias in our estimates? What do you
Because
think?
we have an observed heterogeneity in this case.
Yes, because the unobserved heterogeneity is included in the intercept. So it's not part of the error term. If it's not part of the error term, this means that the error term does not include an information that might be correlated with the explanatory variable. And the worst case that we can have if this UI is correlated with xi is a multicollinearity in this case, because it will be considered as a variable. And we know that multicollinearity does not affect the bias. It can just affect the efficiency of my estimates, but it cannot lead to, or it does not lead to biased estimates. So if the intercept includes the individual effects, in this case, the error term will have a constant variance and will satisfy the classical assumptions that we can have, which means that the estimates in this case are not, which means in this case that the error term is not correlated with the explanatory variable, and that even the UI, even if it's correlated with the other regresses, it will not create a bias. Tahani?
Hello, everybody. I hope that you are all fine.
Thank you.
Actually, Mr. Chahir, I ask about when we should applicate the fixed effect model and why we should apply the random effect model. I mean, there is some science maybe that can help us to choose the right model and the most efficient one.
Very good question. I will just I will come back to this at a later stage after explaining the rationale behind the two models, and then we explain what is the relevance of each one and how to choose between them. So I will just wait for this a bit until we finish the explanation of the theory behind first. Okay?
Great, great.
Other questions? Okay. So that's the first model, which is the fixed effects, okay, that we have here. And we said that we included this UI term in the intercept. If the UI is not included in the intercept, but it is included in the error term, which is what we have here, then in this case, it will be the random effect. And we will see why, in this case, the random effect needs some assumptions, because simply this means that I'm including the individual effect in the error term, and the only condition under which the estimates of the random effects will not be biased is, what do you think? What would be the condition that guarantees that the estimates of the random effects are not biased based on what we have seen? What do you think?
To have a constant variance.
That they have a constant variance, but is it the case here?
And not to be correlated with X.
Exactly, not to be correlated with X. Why? Because if the UI here is included in the error term, the estimates coming from the random effects can be unbiased if the whole all of this error term is not correlated with X. Because if it's correlated with X, this means that the assumption of non-orthogonality is not satisfied, and if it's not satisfied, sorry, the assumption of orthogonality is not satisfied, and if it's not satisfied, we get biased estimates. So that's why, in this case, the random effects model can be used under the condition that the error term is not correlated with the explanatory variables. Okay, and again, for the rest, it will be basically an OLS regression because we have the same intercept and the same slope for all individuals. Okay, so that's just a very general distinction between the way we approach fixed and random effects models, but clearly, if here in this case this U term is correlated with the X, it will lead to a correlation between the error term and the X. And if the error term is correlated with the X, this means that the assumption of orthogonality is not satisfied and that our estimates are biased. Okay? Any questions on this point before I proceed? Any questions? Okay. So in this case, for the fixed effects model, they are the basic and the most important characteristic for the fixed effects model is that they include different intercepts for each individual. And this is in general done by using what we call the dummy variable approach. As I said, I'm introducing in my model a dummy variable for each individual. And if I have 15 individuals, then in this case, I will have 14 dummy variables, for instance. And that's why we can call this fixed effects model the least square dummy variables model, okay? Because it's basically based on the same idea. If you remember, we have seen here in the fixed effects model that I'm basically introducing an individual effect for each individual, which is this UI, okay? So, and this is done through the different dummies that are introduced in the model, and that's why we can call this method as fixed effects, sorry, the least square dummy variable, which is the LSDV, okay? To partially answer the question of Tahani, in general, when it's good to use the fixed effects model, it's good to use such models whenever the individual effects are correlated with the explanatory variables. For instance, if we assume that the enthusiasm is correlated with education, because if I'm enthusiastic, I might reach higher levels of education, for instance. And if this will change from an individual to the other, then they have to be introduced as a fixed effect. Okay? So the first thing that can give us an idea is to use the fixed effects model in the situations where the individual specific intercept may be correlated with the regressives. Because if they are correlated, this means that if those unobservables are part of the error term, then we're going to have the assumption of orthogonality violated, and if it's violated, the estimates will be biased. But clearly, bearing in mind that the fixed effects model is basically a least square dummy variables model, which means that we're introducing dummy variable for each individual. So the more I have individuals, the more I will introduce dummy variables. And the more I introduce dummy variables, the more I will consume the degrees of freedom. And that's why I must have a very large data set in order to be able to run this kind of regression. Because let's assume that we have 3,000 firms that are observed over 2 years. In order to control for all the unobservables at the firm level, I will have to introduce a dummy variable for each firm. So if I have 3,000 firms, I will have to introduce 2,999 dummies. So if I don't have enough observations, I will consume all the degrees of freedom. So if the sample is not large enough, I might be able, or I might be constrained to not include such dummy variables. That's why the most important thing whenever we run this kind of regression is to have a large sample as much as possible. That's a practical point, but the important and conceptual point is whenever we have a correlation between those unobservables and the regressors. Okay, so that's what you can see here in this graph, where let's first look at the dotted line that we have here, okay? And that shows a positive correlation between X and Y, right? So here, if we have this correlation between X and Y, and it's positive, we might see that, or we might say that the slope of this line is equal to, let's say, gamma. What is the problem of this gamma, that is my slope? Is that it does not take into account the individual characteristics of the blue and the red individuals, right? So in this case, if I rerun the regressions and take into account the fact that each individual has a different slope, alpha 1 and alpha 2, based on what we have already seen, then I will be in this case having two different intercepts and a new slope, which is beta. And we can see here that the beta is the same for the two individuals. That's on the one hand, but on the other, this beta that we estimated is not similar to the gamma that I'm talking about here, which means that if I do not take into account the fact that alpha 1 and alpha 2, which are the two individuals, they have two different intercepts, the gamma will be a biased estimate of the relationship between X and Y, because the unbiased parameter in this case is beta. Okay, so is it clear why, if we don't take into account this unobserved heterogeneity, then the estimated slope will be biased? Is that clear? Any questions? Any questions? Any comments?
No, all clear.
Okay. So, so here, by introducing by introducing those individual fixed effects, we control for the unobservables, and consequently, we avoid having biased estimates. Just a second. Moving now to the random effects. So for the random effects, it's easier, even though we have also to take into account an important point. So we have seen that the fixed effects model, it assumes that for each individual or for each group or unit of analysis, okay, we can control for any time invariant characteristics embedded in the individual or in the firm or the household and so on. Yet, some unobservables can be random, so they are not that they are stochastic or they are not predetermined, if you want. So that's why the random effects model attempts to deal with the case where those unobservables are random or are stochastic. That's why we call it the random effect, because it's not fixed over time like what we have seen in the first model. Okay? So in the random effect in this case, we assume that the intercept of an individual unit is a random draw from a larger population with a constant mean, which is more or less what we assume in the case of OLS. So the advantage of the random effects compared to the fixed effects is that it does not use as much as degrees of freedom. So it's not it does not consume a lot of degrees of freedom, which is the case of the fixed effects model. So that's why given that we do not introduce those dummies like what we have done in the fixed effects model, it might be more relevant in the case where we don't have, first, when we don't have a large data set, that's on the one hand, because we do not introduce a lot of dummy variables, and therefore we do not estimate a lot of parameters. And then, conceptually speaking, in which cases we can use the random effects model? We can use it in the case where my regressors are not correlated with the unobserved heterogeneity, okay? Or where this random intercept of each cross section that we have in my data is not correlated with the explanatory variables or with the regressors that we have, okay? And clearly, if I have some time invariant variables, they can be introduced in the random effects model, but not in the fixed effects model. Why is that the case? So back to what we have been talking about, I will take, I will assume that we're running a survey for different individuals. So I will ask Rashida, what is your gender? So she will respond, female, in my survey of 2015. And then I ask her again in 2020. I do the same with Hassan, I do the same with Zahra, and so on. So for all of you, given that the gender is time invariant, it did not change over the 5 years, in this case, the gender variable will be captured by the fixed effect. So if I introduce a dummy variable for Rashida that takes the value of 1 and that is 0 otherwise, another dummy variable for Hassan, it will take the value of 1 and 0 otherwise, a third dummy variable for Zahra, it will take the value of 1 and 0 otherwise, and so on and so forth. So in this case, all the time invariant variables will be captured by this fixed effect, by those fixed effects. Which means that if I'm interested in my study in examining the effect of some time invariant variables, like the gender, for instance, I cannot use the fixed effects model, because the fixed effect model will, all those time invariant variables will be automatically captured by the fixed effects. And so the gender will be captured by the fixed effect. My location, if I don't change location over time, it will be captured by the fixed effects, which means at the end of the day, any time invariant variable will not be included in the model, because it will be solely measured by the fixed effects. Okay? Any questions on this part before we proceed?
Ask a question, please.
Yes.
When we say time invariant, is there a limit for that? Let's say we have a household survey and we check the gender of household head. So it's not likely that the household head changes, but there's still a possibility. So like if we check the gender of the household head, should we consider it as a time invariant or time variant? So
Well,
the gender doesn't change, but it could be a different person. The household head might change.
well, I mean, as long as it changes, then in this case, it's time variant.
Okay.
If it's the same, I mean, let's assume that we have two households and we decided to use a fixed effects model, okay? So for the household whose head remained the same over time, in this case, it will be captured by the fixed effects.
Yeah.
If the head of the household did change, then in this case, it will not be captured by the fixed effects. Other questions?
Thank you.
Okay. So this means that back to this first equation that we were talking about, here the error term includes also the new because the UI is part of the intercept. Here the UI is part of the error term, which means at the end of the day that there is some individual effects that are included in the error term and that might make the error term non-constant. Sorry, the variance of the error term might not be constant. And if you remember from the basics of econometrics, whenever we have an error term that is not constant, which means that it suffers from, if its variance is not constant, which means that it's heteroscedastic. In this case, in order to resolve this problem, we have to use the weighted least squares or the generalized least squares, and that's what we're going to see in a few minutes. So as I said, the random effect model has the following composite error that includes the UI and the V, as you can see here, okay? So in this case, we have the U and the V that are the two components of the error term, which means in this case that I'm going to have a variance. The variance of the error term will include two variance estimates, sigma U for the first one and sigma V for the second one, right? So for the first one, it will be varying across individuals, which means that at the end of the day, the error term, the variance of this error term overall will not be constant. And if it's not constant, it is heteroscedastic. And if it's heteroscedastic, we have to resolve this problem using the generalized least squares. So how the generalized least squares is run, just a quick reminder. I'm sure you have already seen this, but just to understand the rationale behind the random effect. So that's for the GLS. In general, what we assume in the OLS is that the variance of the error term is constant. If, as you can see on this graph, here we don't have the same variance for all for different parts. As you can see, they have different sizes, which means that at the end of the day, the error term does not have a constant variance. And in this case, the source of variability and the size of the measurement error that we have can be proportional to the measured quantity. So we can see here for higher values of x's, there is a larger variability. So here there is the lowest variability. Here we have the largest variability. And that's why in this case, the variance is a function of the mean. And that's why the variance of the error term is not constant. How to resolve for this problem? I will just use a very simple example to show you how we can resolve for that before we break. So let's assume that I have the savings equation that is equal to beta 0 plus beta 1 income plus the error term. And we assume in this case that the variance of the error term, here the u, is known. And it's equal to sigma square multiplied by income, which means that the variance is a function of income itself, right? In this case, is the variance of u constant or not? What do you think?
It's variable.
It's variable because it depends on income. So that's why if it depends on income, then the variance of u is not constant. And if the variance of u is not constant, then we have to make it constant. So I will introduce a weight in my regression by dividing all the variables by the square root of income. Why the square root of income? Because here it's the variance that is function of income, so which means that the standard deviation is a function of the square root of income. So if I divide all the variables that we have here by the square root of income, in this case, my new error term, which is k, does not include the income anymore, which means that its variance is constant. But now all the variables will have to be expressed as the square root of income, right? So the idea here of the generalized least squares is that I will give a weight, or I will introduce a weight that is measured here through the square root of income in order to get rid of this variable component of the error term. But clearly, this means that I have to know what is the structure of the variance, because if this variance is unknown, I will not be able to determine the weight, which is more frequent because rarely we can know how the how this equation looks like, right? So in this case, we estimate the transformed equation by OLS, and that's the last equation. And we call it generalized least squares because why it's generalized? Because it's the general case. In the first case here, we assume that the weights are equal. But now once we introduce the square root of income, weights are not the same. So that's why we call it the generalized least squares or the weighted least squares. And it provides, we know that heteroscedasticity does not affect the biasness of the result, but it can affect their efficiency. That's why the weighted least squares or the generalized least squares can affect, the generalized least squares can lead to more efficient estimates compared to those that are used with the OLS, and therefore we can use the t-test, the f-test, the confidence interval, the p-values, and so on. Okay? So the GLS estimator in this case to correct heteroscedasticity is called the weighted least squares estimator, where we're going to minimize the sum, the weighted sum of the squared residuals. And in the example I showed you, it was the square root of income, okay? Which is the inverse of the variance, in the sense that, what's the conceptual idea behind that? Is that we want to give less weight to observations that have a higher error variance, because the higher error variance should be given a lower weight in order to make the results more accurate and to make them more efficient. So that's why we're going to assign lower weights to observations that have a high error variance. That's why we call it the weighted least squares. While for the OLS, it gives all the observations the same weights, regardless of the size of their error variance. Okay, so that's why for the weighted least squares, if I will assign lower weights for the individuals that have a higher variance, and if I do not know the function that for the, like the example that I gave you here, the weight in general we can use is the inverse of the variance itself. Okay, so if we do that, if we know the variance, it's easy. But if we don't know the variance, then it becomes complicated. So that's why we need to estimate those weights. How we can estimate those weights? And that's what we call the feasible GLS, the feasible generalized least squares. Because in general, why they are not feasible? Because the formula or the mathematical function of the variance is unknown. And if it's unknown, we have to find the alternative. So we start with a flexible model where we assume that the variance of the error term is equal to sigma square, the exponential of delta 1, delta 0 plus delta 1 x1 until delta k xk. And here, what are the weights? The weights are measured by all this part. So they are measured by the exponential part. In order to make those weights known, we have to find the values of delta, right? So here, as if we have a new econometric specification that we want to estimate, where the dependent variable is the variance, and I will regress this on x's in order to get the deltas, and then I will find the errors. So that's what I mean, what we do have here, given that the delta must be estimated. So if the delta must be estimated, how we're going to proceed? We're going to transform the above as following, where the UI is the error term, sigma square is the constant, and then the exponential of the different variables plus the new error term. If we take the log of all that, it will be the log of u square plus alpha 0, which is the log of sigma square, plus why I have here the exponential in order to get rid of the exponential with the log. And here we have delta 1 x1 until delta k xk plus the new error term. So alpha 0 contains the original intercept, which is log sigma square. And this new error term has an expected value of 0 and is independent of x, which means that the orthogonality assumption is satisfied. If we don't observe the error term, we can replace it with the residuals. And now we can estimate this relationship using OLS. Once I estimate this using OLS, I will get the value of all that, which will give me the value of the weight, which is H, right? And that will be used in the weighted least squares, right? So at the end of the day, in the generalized least squares is used in the OLS, is used in the random effects model, and that's why we can call the random effects model generalized least squares model, in the sense that we give smaller weights to observations that have a higher error variance. And again, we are correcting here for the efficiency, which means that to start with, my error term has to be uncorrelated with the explanatory variable. Okay? While in the fixed effects model, it's more of a strategy of dummy variables. That's why we call it the least square dummy variables. So that's generally the theory behind the two models, where on the one hand, we have the fixed effects with the least square dummy variables, the random effects with the generalized least squares, when we use the fixed effects when the unobservables are correlated with the explanatory variables. If the unobservables are uncorrelated with the explanatory variables, then we can use the random effects. Okay? Any questions on this point?
Please, Dr. Chahir,
Yes.
I can see that when we cannot verify all assumptions of OLS in fixed effect, we can use generalized least square.
No, sorry, say it again, please.
When we cannot verify assumptions of heterosidicity for fixed random, we can use the generalized least square.
No, it's no in the random. I mean, heteroscedasticity is basically more present in the random effects model more than the fixed effects model. In the fixed effect model, it's basically an omitted variable bias. So that's why the fixed effects in general they correct for this omitted variable bias.
Okay. And what about the robust weighted least square? Robust weighted least square. If it's the same of generalized least square?
In general, of the generalized, it deals in general with the weights that you attribute in order to make the variance of the error term robust.
Why? Why we need to make it robust?
I mean, it's not. I mean, we do in case that the standard errors are not robust or they are driven by some heteroscedasticity, they are driven by different factors, you have to do that. But if they do not suffer from this problem, then there is no need to do it.
Okay, but when we estimate generalized least square, we not need to verify heteroscedasticity.
No, because
think.
because actually it's done in order to address the problem of heteroscedasticity.
Okay, thank you.
Other questions? Okay, so before starting this new section, perhaps it's time to break. Now it's 6:25 Cairo time. We will start in 15 minutes with a recap and how to choose between the models and then some data applications. So have a nice break and see you in 15 minutes. Now the last part is to see how to choose between them. And then we proceed with the data application. As I said, we will send you tomorrow or after tomorrow at the latest the different do files the different do files in addition to the slides and the readings. Okay. So in order to choose between the two models, and I remind you that the fixed effects model is primarily based on a model with fixed effects. The random effect is basically a generalized least squares model. So to choose between them, we're basically trying to choose between first, shall we use a fixed effects model or an OLS? And then shall we use a fixed effects model or a random effects model? So in order to choose between them, as I said in the beginning, the fixed effects model is simply an OLS model with individual dummies, and that's why we call it the fixed effects least squares model. And we can test it against the pooled cross-section model using a normal F-test of the joint significance of dummies. You know, as if we're comparing two models with different sets of variables, and in this case, we compare the two models, the pooled one and the least square dummy variables, one relative to their degrees of freedom, using their R squared. And this is the classical formula of the F-test, where the degrees of freedom that we have are n-1, which is what we have in the numerator, and t minus n minus k, which what we have in the denominator, bearing in mind that n is the number of individuals that we have, t is the number of periods we have, and k is the number of parameters to be estimated, right? So here we're comparing the R squared of the least square dummy variables minus the R squared of the poor dummy variable. And again, it's the classical formula of the F statistic. And in this case, if we do this, we're comparing the explanatory power of the least square dummy variable relative to the pooled one. And the higher the value of the F-test, in general, the reference value is 10 by convention. In this case, the least square dummy variable is, in this case, there is a significant difference between both. And in this case, we have to use the least square dummy variable, which means that the fixed effects, they do matter relative to the OLS estimate. Oh, sorry, or to the OLS model. Another test that could be also used is to test the random effects against the pooled cross-section model. And so I remind you that the main difference between OLS and the random effects model is how the variance is treated. And that's why testing for the random effects model against the pool cross-section involves mainly the tests that deal with heteroscedasticity, such as the Broch-Pagan-Lagrange multiplier test. And while in the first test that we have seen, we use the F-test. Here, in this case, it's essentially a chi-square test, where we have 1 degree of freedom that the variance of u is equal to 0, which means that the composite error term that we have seen, that was sigma square u plus sigma square v, will be reduced to the regular independently and identically distributed error. Okay. So in this case, basically what we do for this Lagrange multiplier test of the correlation of error term, we have the two hypotheses. The H node, where the expected value of the error term of UIT multiplied by UIS is equal to 0. So again, this variance of U is equal to 0. And H, the alternative, so the alternative hypothesis is that it's not equal to 0. If we reject the H node, this means that the sigma square U is not equal to 0, and therefore, in this case, if we reject the H node, we cannot use the OLS. If we do not reject the H node, this means that the sigma square is equal to 0, which means that the composite error will be reduced to the normal error term that we have. So this test statistic that follows a chi-square distribution with 1 degree of freedom is calculated, as you can see here at the end of the slide, where the Lagrange multiplier will be calculated depending on the number of individuals, the number of periods or time that we have in our data set, and then different calculations for the error term. So if this test statistic exceeds the critical value that comes from the classical tables, then in this case, the OLS should not be used, and we have to use the generalized least square, because in this case, the generalized least square will assign different values for the different weights, sorry, for observations that have a higher error variance. Okay. Another important thing is that I remind you that in the first test, for the F test that I showed you before, we were comparing the OLS relative to the fixed effect, right? In the second test, I was comparing the OLS relative to the random effect. In the fourth one, I'm comparing the fixed effect relative to the random effect. And here, the rationale behind the test is very important, because I remind you that if I have to use the fixed effects model, but I use the random effects model, in this case, my estimates will be biased. Why? Because the fixed effects model control for the omitted variable bias, which means that when I'm comparing the fixed effects model relative to the fixed effect relative to the random effect, I'm comparing whether the fixed effects will lead to more consistent estimates, because in this case, the random effect will lead to biased estimates, or in the case where both of them will lead to consistent estimates, which one will lead to more efficient estimates? And in this case, it will be the random effects model. And this is very important, because in general, between biasness and non-efficiency, biasness comes first, or it has to be treated first. So that's why the null hypothesis of the test, which is the classical Hausman test, the null hypothesis is that the individual unobserved effects are not correlated with the variables. If that's my null hypothesis, so if I assume that the individual fixed effects are not correlated with the explanatory variables, if I do not reject this hypothesis, this means that I have to use the fixed effects. So, sorry, if they are uncorrelated, sorry, the null hypothesis is that they are uncorrelated. If I reject this hypothesis, this means that they are correlated. And if they are correlated, this means that I cannot use the random effects, but I have to use the fixed effects. So that's why in the random effects, sorry, in the null hypothesis of this test, I remind that the null hypothesis is that the individual's unobservable effects are uncorrelated with the regressors, which is the assumption that we have in the random effects. Because I remind that in the random effects, we assume that the regressors are uncorrelated with the unobservables. But if the null hypothesis is not rejected, which means that in our case, the unobserved effects are not correlated with the regressors, then in this case, I can use the random effects. Okay? So in this case, I'm comparing the estimates from both models and to see whether one of them is consistent or the other is efficient. Okay? So the way the test is constructed, again, it follows a chi-square distribution, where I'm comparing the estimates coming from the least square dummy variable relative to the estimates B here in this line. Okay. I'm comparing the estimates coming from the least square dummy variable with the estimates coming from the random effects. They are multiplied by a certain weight, and I'll come back to that later, and then the estimates once again. And as I said, they follow a chi-square distribution. This weight W hat -1 is basically comparing the variance of the two estimates, those coming from the least square dummy variable and those coming from the random variable. So if we reject the H node of this test, we have to use the fixed effects, because in this case, we reject the fact that they are not correlated, which means in this case that if we use the random effects, our estimates will be biased and we cannot use the random effects. Okay, so far, to wrap up this part, for random effects, they are efficient because they are estimated using the generalized least square method. In general, the most important assumption is that the unobservables are not correlated with the regressors, and it has also two advantages. First is that it can deal with the regressors that are time invariant, as I said, and second, it does not consume a lot of degrees of freedom. For the against the random effect, actually it's a very strong assumption in the sense if we assume that the unobservables are not correlated with the regressors, because in reality they might be correlated, and in most of the cases they are correlated, which means in this case if we use the random effects, we're going to get inconsistent estimate due to this omitted variable bias, and that's why it's important to use fixed effects. Okay, even if the fixed effects are inefficient, but what's more important than being inefficient is that they are consistent. Okay. So that's a brief introduction of the fixed and random effects. Before moving to the data application, any question, any comment, anything that's not clear? Any question?
Just a general question, Shahir, not directly related to the fixed random effects. So when the degrees of freedom decrease, that would make our model less attractive. But generally, when we add more independent variables that we think are relevant to the model, then this is the better specified the model is. How can we work around this generally?
Well, I mean, at the end of the day, the most important criteria would be there is always a trade-off between the sample size and what is introduced in the model, because clearly if I'm constrained by the sample size in the sense that my sample is limited and I will have to be very careful in order not to lose a lot of degrees of freedom, then in this case I will be constrained by the number of variables to be introduced. But clearly, if I'm using a microeconomic data set, firm level data or household data or labor force survey, we're talking about thousands of observations. So that in this case, there is no we don't have this fear of reducing a lot of degrees of freedom because we have a large sample, which means that in this case the choice of the variables will be based either on the theory or the literature.
Okay, thank you.
Other questions? Okay, so if we don't have more questions, for the application, I will proceed in two stages. I will first show you something without a do file. I'll just show you the output of Stata just to understand what we get. And then we move to the do file and the data set that I will share with you at a later stage. Okay? So for the Stata application, that's in general for those who are already familiar with Stata. For the command that we run, it's xtreg. And in this case, before running such a command in Stata, or I will keep this for later. I just want to show you now what we have seen in the theory itself. So the command that we run is xtreg, and I will explain this later, where the dependent variable is y, the independent variable is x1, and here we specify fixed effects. In general, if we run a regression without specifying at the end comma fe, by default Stata will run a random effect model. Okay, so here, given that we specify that it's a random effect, that it's a fixed effect model, so we get here a fixed effect model with the R squared, and as you can see here, the correlation between the error term and or sorry, the unobservables and the regressors is not equal to 0. It's equal to negative 0.5, which means that in this case we assume that there is that we can have a correlation between the unobservables and the explanatory variables. Okay, then we have the other classical statistics that we get: the number of observations, 70, the number of groups. So here that's the number of individuals, which means that we have 7 individuals and 10 years, right? And then here we have observation per group. We have 10 observation per group, so 10 observation per individual. On average, it's 10, and the maximum is 10, which means here that we have a balanced panel. Here we have the F statistic, and as long as here the probability is less than 0.5, it means that the model, the coefficients included in the model are significant or are different from 0. Then we get the classical table with the coefficients, the standard errors, the t, the p-value, the confidence interval. So here there is nothing new. The classical table of Stata that you have definitely seen before, right? So far, this first part of the table until this line is not new. So what is new is the correlation, right? The fact that it's a fixed effect model, that's the second thing. And the third thing is that we have observation per group because we have a panel dimension, right? What is important in this graph, in this table, sorry, is the second part, the sigma u, the sigma e, and the rho. So what is the definition of sigma u, sigma e, and the rho? The sigma u here, it's the standard deviation of residuals within the groups. Okay, so within the group, within each group that we have, what is the standard deviation? And then the sigma e, it's the standard deviation of the overall error term that we have in the regression. So what is the rho? Rho in general, it's equal to sigma u square divided by sigma u square plus sigma e square. So it's the standard deviation of residuals within group to the power 2 divided by the sum of both of them. So how we can interpret this rho? So here the rho that we have in our model is 0.29, which means that almost 30% of the variance is due to differences across the panels, and the rest is due to the interclass sorry, the differences within panel. Okay, so again here the 30% of the variance is due to the differences between the panels, and the rest for the within panel. That's the outcome for the fixed effect. If we look at the other table with the random effect, sorry, here it's an interesting, perhaps I will show you first. Yes, the random effect, again, it's more or less the same thing, but the main differences here is that here the random effect, the correlation UI and X are equal to 0. And it's assumed, as you can read here, right? So here the correlation is equal to 0. We have the same number of observation. We have the same number of observation per group. And again, we have sigma, the sigma E and the rho, right? And which is the same interpretation, because here it's the fraction of the variance that is due to individuals. Sorry, to the standard deviation of individuals. Okay. So in this table, as you can see, we have here an assumption of a zero correlation between UI and X. Then we get the estimates with the standard deviation, the p-value, the confidence interval, and in general, what tells us also that the model is significant or not, which is a bit similar to the F test that we have seen in the previous slide. Here it's the walled key test. And in order to have a significant model, this probability of chi has to be less than 0.05, which is 5%. So we can see here that the model here is not significant. And this perhaps shows that we might want to check whether the random effects model is better. And that's what we do in the next stage, where we're going to compare the random effects with the fixed effects. And the way we run the Hausman test is XT-reg. So we run first the fixed effect, and here the order is important. So we run the fixed effect model, we store the results, then we run the random effects model and we store the results, and then we write Hausman fixed and random. So fixed, that shows the results coming from the fixed effects model, and random, sorry, that shows the estimates coming from the random effects model. Here, when we run this, as you can see, we are comparing be consistent under H node, and I remind you that H node here is that X and the error and the individual effects are uncorrelated. Okay, so if we reject the H node, then this means that they are correlated, and if they are correlated, we have to use the fixed effects. So based on these two estimates that I have shown for the fixed and for the random effects, here we have to use the fixed effects because the probability of the test is significant, which means that the fixed effects gives consistent estimates, even if the random but the random effects will give inconsistent estimates. Okay. And if we reject if we do not reject the H node, this means that we're going to use the random effects because they give us more efficient estimates. Okay. So that's how Stata looks like when we use the fixed, the random, and the Hausman test. Two final remarks before we move to Stata. I just want to show you also what happens when we introduce the dummies, because if you remember, I told you that the fixed effects strategy is primarily a least square dummy variable model. And that's why if we introduce the random effects, sorry, if we introduce dummies in an OLS, we can get the same estimates. So here, what I will do is that given that we have 7 groups, we can introduce 6 dummies. So we can run this through 2 methods. Either we run the areg command, and the areg command is the regression command with some fixed effects that will be absorbed. And here what we tell data is to absorb the country fixed effects. So we run areg with the outcome variable, the dependent variable, and we absorb the fixed effects. So here we get the x1 and the constant, and if we compare to the values of the coefficient we get here, they are exactly the same. Okay, but the difference is that here I use the data as a panel data with a panel command, which is xtreg. Here I used an OLS, but with all the country's fixed effects. And that's why, again, we call it the least square dummy variables. Alternatively, what we can do is also to run an OLS with explicitly the dummies, and that's what we get exactly the same result. But the command in this case will be we run xi, then regress y x1 I dot country. If we write it this way, we're going to get I dot country, where we ask Stata to introduce all those country dummies explicitly in the model. So the difference between this command and the previous one is that in the previous one, we absorb those dummies. Here, we keep the dummies in the table. That's why in this table here, we don't have any dummies, right? But in the, sorry. But in the next table, we do have those country dummies. Okay. So those are the main Stata outcomes that we get. So again, to sum up all that, 5 main points to sum up the Stata part before we work on Stata. First, the commands that have to be used, they start with xt, and xt refers to the set of commands that deal with panel. Second, it's important to distinguish between what we obtain here in terms of the correlation between u and x, whether it has a value or it's zero. It has a value if we're talking about fixed effects, and it's zero if we talk about random effects. Third, we get also some statistics on the sigma u, sigma e, and the rho that shows the variance that is due to differences across panels. Fourth, if we replace the fixed effects with an areg with the dummies that are absorbed, or we introduce them in the regression with the I dot command, we also get the same results exactly. And finally, to choose between them, we run the Haussmann test, and in the Haussmann test, it's very important to keep the same order that we have in the estimation, right? And I remind you that the null hypothesis here pertains to the fact that the x and the individual effects are uncorrelated. Any questions? Anything that's not clear before we move to the applied part? Any questions? Okay, so let's move to the applied part. And for this applied part, now you can see Stata or not? Can you see Stata?
Yes.
Yes, yes.
Okay. So here, the data set we will be working on is the Egyptian labor market panel survey. that was collected by CAPMAS and the Economic Research Forum. And here we have the data for 3 rounds, 1999, 2006, and 2012. And as you can see, we have a lot of variables that measure the characteristics of the labor market over time. And we're going to see in this do file that I will share with you what are the main commands that we can use when we work with a panel data. So before I start, has anyone worked with labor force survey before? Or firm level survey?
I didn't.
Anyone did?
Yes, I've done some work on firm level survey data,
Which data?
enterprise surveys.
For one country or for different countries?
Actually, I've used it for one country. It was a cross section of Lebanon. I was working on innovation. Now I'm working on a panel of different countries, MENA countries, basically.
Okay. For the World Bank Enterprise Survey, it's a very good data set because it includes different variables at the firm level, and they are harmonized. They can be used to compare different MENA countries as well. Their only drawback is that the panel dimension in these data sets is a bit small, almost weak in most of the countries. So that's why, in general, when it comes to the identification strategy, you have to think thoroughly how to make sure that we have those causal relationships between different variables. But otherwise, it's a really good data set. Rashida?
Please, can you share with us the link of the data? I want to download it.
Yes, you will receive all this at the end of the training. I will send the do file and the data.
I mean the link, when we can find the data.
I mean, you can find the data on the website of ERF, but until your request is approved, this can take a few days. So you will receive a folder with all the data sets that we use in the training, in addition to the do files and the slides.
Okay, thank you.
Okay. Well, so to move forward with this, so here we're using an individual data set or a microeconomic data set, which is the Egyptian labor market panel survey for 3 years. Now we have a fourth year, which is 2018, and we're in the process of collecting a new round, which is the one of 2023, 2024. And the advantage of this data set is that its panel dimension is very good. So it's a bit large sample of individuals that are observed over different periods, which means that we can apply all those techniques that we have seen today. So in general, what I will show you in this do file, and you will receive it also to see what are different commands that are done, and how we can analyze the data that we have. Clearly, to start with, in line 15, you can see it now. It's a bit larger. So the first command is cd, because cd will locate the directory that we use, right? And then we can start a log file, right? in order to include all our results. So if we run this, we will see here in Stata that a log file is launched, and if the log file is launched, we will be able to store all the results, right? Then we can run a very simple command, which is D. If we run D, Stata will describe the results. So D here stands for describe. And by describe, I mean to ask Stata to tell us what are the variable name, the storage type, whether it's a string variable, it's a text, or it's a number, how it's displayed, and what is the label of the variable. So the variable called round is the round of survey. End ID, it's the unique individual ID. HHID, it's the unique household ID, and so on. So we have this for all the variables, right? Once we started the log and we run this describe file, we can also ask Stata to give us more details about a specific variable, which is the code book. So if we run code book and we write the name of a variable, here what we get, fin DID, it's the unique individual identifier, and then we have how many values, how many missings, some examples, and that's it. So the code book gave us, and then what's the type of this data set here? String, it means that it's stored as a text, because those are the IDs of individuals, right? So the code book gives us the details of each variable if I want to understand the values, the missings, and so on, right? I can also ask Stata to check for the duplicates in case I have the same individuals that are observed in the same round, in the same survey. So if I run this command, what we get here, what do you think? Can anyone interpret this table? Do we have duplicates here?
I think no.
Yes, we don't have any duplicates, because we are told that the surplus is equal to 0, and we have zero surplus. Okay. So that's the command that helps us, and this is very important whenever we work with panel data, because in some cases we can have some duplication, and if we have some duplications, Stata will not be able to run any panel command. So now we're going to see the first variable that we're interested in, which is this one. So what is the variable that we look at? It's the real hourly wage of all jobs. Okay. In 2012 prices, which means that given that we have different years, we want to make sure that there is no inflation in in our calculations. So we deflate all the prices with the prices of 2012. Okay. So that's our variable. It's a float variable, which means that it's variable based on numbers. That's the label real hourly wage of all jobs, and that's the name of the variable, right? If I run summarize and then the name of the variable, we're going to get some descriptive statistics for the variable. So the number of observations we have, the mean of the wage, the standard deviation, the minimum, and the maximum. Okay. Then what we're going to do later is a new command. This new command that you can see in line 50, I mean, so far I haven't done anything related to panel. I'm just getting more familiar with the data, right? So here, what we're asking Stata to do is to construct a table is to have the different rounds where the age is greater than 15 and lower than 64, okay? And then, because why between 15 and 64? Because that's the working age. And then a certain variable called car MPSTP. So it's important to understand what's this variable. So I will write D car STP, which is the employment status of the primary job, and the reference week is equal to 1. So if we run tabulate car STP, we have the different possibilities. We have wage workers, we have employers, we have self-employed, and we have unpaid family worker. Okay? So clearly, if we're interested in wages, it's the first category that we can rely on, which is wage worker. So I will ask Stata to table round if age is greater than 15 and less than 64, the working age, and for those who are wage worker, sorry. Okay. Then we have here a very important command, which is PW equal expand. Expand, that's the expansion weight. So we're going to have a table where the rows are the rounds and the content will be the mean of the weight, the mean and the median of the wage. And clearly, here I'm using the weight, because different individuals in the same data set, they don't have the same weight. They have different weights. So for instance, in my data set, an individual with the characteristics of Evren can have a higher weight than an individual with the same characteristics like Hassan. Okay? And so on. So it's important to reflect the weights in my descriptive statistics. So if we run this command, table round for the working age and those who are currently working, here we have, as you can see, the different rounds, 1988, 1998, 2006, 2012, with the mean wage and the median wage. Okay? We can go a step further and perhaps run this by gender if we want, or by education level, and so on. Okay? Perhaps just to give you an example, for this command, again, we're going to use the same criteria where we're focusing on those who are working between age and 15 and 64. For those who are wage worker, so current employment status is equal to 1. And we use the expansion weight in order to reflect those the weights that we have in the population. And we want to tabulate the education with the employment for each round. And that's why we start the command with by sort round. So by sort round will give us the results of each round. So if we run this, we're going to get, for the first round, 1998, the educational level, illiterate, elementary, middle, general, vocational, and so on. And the employment status, whether they are wage worker, employer, self-employed, unpaid. And here we have the cross tabulation for each round. So we can see how this has evolved over time. Okay? So all this, we're just running some descriptive statistics over time in order to see the characteristics of what we have. Any questions so far? Anything that's not clear?
I just had a question about weights. How are weights defined in this data set?
So the weights in general, they come from the sampling frame. So in general, in order to make the sample nationally representative, at the governorate level, at the industrial level, at the sectoral level, at the regional level, it depends on the level of representativeness. Each individual is assigned a weight, and this weight has to be taken into account in the regressions and in the descriptive statistics. So in general, the weights are done from the sampling frame or through the statisticians who work on the survey itself. And
when we
in our
download,
data set, here it's the name of the weight is expand. For instance, in the World Bank Enterprise Survey, the weight is called W median or W. There are three weights in the World Bank Enterprise Survey: W median, W maximum, and W minimum. So those are the weights. Okay. You will see in the doc file that there are several descriptive statistics that you can run. I will not go through all this because there are several things that you can do with, and it can give you also different ideas about what can be, what type of commands can be run. I just want to move to the regression part because that's what we're working on. So one of the first commands that are interesting, or one of the first things that to analyze, is the variable called atr 98, 06, and 12. So if I run this command, here we have the sample size of my data set. And we have individuals that are included in the three panel rounds: 1998, 2006, and 2012, 39,000 observations, right? Then those that are included in 1998 and in 2006, but not in 2012, 8,000. Those that are included in 1998 only, 6,000. Those that are included in 2006 and 2012, 31,000, and so on and so forth. Okay. So that's why in this case it's important to analyze this to make sure that we know how many individuals are included in all the rounds of the survey that we have. Okay. So that's the first thing that we analyze in the panel. What we're going to do later, we're going to ask Stata to keep only those that are in the three rounds or in the two recent rounds. Okay. So we're going to tell Stata keep if attrition is equal to 1998, 06, 12 equal to 1 and equal to 4, which means that if I rerun the attrition command once again, if we run the attrition command once again, we're going to have only two values, which are 1 and 4, right? And then I will ask Stata to keep only two rounds, which are 2006 and 2012. So which means that I will get rid of the older rounds. So if I run tab round, we're going to have only two rounds. And here, probably, not probably, but here we have a balanced panel because we have all the individuals that are observed in the two periods, right? And then we're going here to keep only the variables that we're going to use: the individual ID, the employment status, the wage, education, the wealth index, the round, the current employment status, and the year of the first job. Okay. So here, as you can see, on the right, the number of variables that are included here now has decreased. Why? Because we only kept in our data set the variable that we are interested in. Okay. Back to what we have here. So here, how many rounds? Again, we have 2 rounds. There is a command in Stata that is called reshape. I don't know if you have previously used it, but I will show you also an important command that we have to use in Stata, which is the help command. So if I run help reshape, we're going to get this. So in several cases, our data can be either long or wide. Long, it means that I observe the same individual in the first year followed by the second year. So here, when it's long, it's in the panel format that we want to use because I have I. So for instance, Hassan in round 1, Hassan in round 2, Rashida in round 1, Rashida in round 2, and so on. In some cases, we want to reshape from long to wide. So I want to have Hassan followed by Rashida here in year 1 and here in year 2. So in some cases, if my data is long, I want to reshape it to become wide. In some cases, it might be wide and I want to use it as a long data set. But in all cases, for the panel regressions, we use in general the long, not the wide. Okay. So here, that's the command that we have, which is reshape. So reshape wide, current employment status, real wage, education, wealth index, year job, where we have the round and the ID. So here we're going to reshape from long to wide. So instead of having a panel dimension, we're going to have it a wide data set. I'm not doing that because we're going to use it in the panel, just to show you that we can do it. But what we want to do is to have a long data set as it is. So I will just keep this command. I will not run it because what we're interested in is the long version, not the wide version. Okay. Let's create now our variable, which is the log of wage. So we're going to create the log of wage. And clearly we have a lot of missing values because not all individuals are working. If you remember, we had those who have those that are self-employees, unpaid care, etc. So that's why if we create the log of wage, we're going to have some missing values. And that's what we see here. We have around 44,000 missing values. We already did this. We are going to keep round of 2006 or 2012. And it's normal that we have 0 observation deleted because we just have this variable, these 2 rounds, I mean. Let's move to the regression. Okay. So if we run the model in a I have to reload the file again because I dropped some variables. In just a second. So here, again, we're going to do the same thing. So want to get rid of that. Voilà. So we're going to generate the variables that we need in our model. So again, we're going to run the log of wages. We're going to keep only 2 rounds, okay? And then we're going to create some explanatory variable. For instance, a variable on the work stability. And then, so here we created a variable on work stability, permanent, temporary, seasonal, intermittent, and so on, okay? And then we're going to create a variable only for those irregular workers. You will see all the details in the do file that you will see, but here I'm just creating the variables as an exercise in order to use these variables later in my regression. Then I want, for instance, to include those who are working in the private and those who are working in the public sector, their economic activities, okay, in order to create the sector where they are working. And then we're going to create a gender variable that takes the value of 1 if the individual is a female, then the years of schooling, and so on. So all these covariates will be part of uh, our model at the end. Okay, so for the years of schooling and for the gender. Now we have 2 things to do. We're going first to run a regression with an OLS. So that's first to summarize with the main statistics that we have in the data set. So as you can see here, a lot of variables are binary with 0 and 1. And then other variables are continuous, like the years of schooling, like the wage, etc. Okay. And then if we run this regression in line 395, as you can see, is this regression in line 395, is it a panel or an OLS regression? What do you think?
I think OLS
It's
regression.
OLS. Why OLS? Because we don't have the XT.
Reg, yeah.
Yes, because it's reg. So if we run this regression, we're going to get this outcome where the years of schooling, female, stability, public, and then some economic activities are statistically significant. Other economic activities are insignificant, and the constant is significant, right? So here it's an OLS, but the problem is that I don't take into account the characteristics of the individuals over time, because I didn't specify that they are that it's a panel data set. So that's why we're going to keep the individuals if they are both in 2006 and 2012, okay? And we're going to run the regression once again, right? Yes, I forgot to run a certain command here. Okay, because here I want to introduce the time dummy. But so far, all these regressions, as I said, OLS regressions. So now what we want to do is to run the regression for the panel. So what we're going to do is to declare first that it's a panel, and to do so, we're going to run an xtset command in order to declare that it's a panel, right? And we can run the xtreg command. So if we do so, we're going to see that we get exactly what we are talking about, the random effects, because we specified that here it's a random effect. The correlation is equal to 0, assumed, and it's a GLS regression, so the generalized least square regression, right? Here the maximum is 2 observation per individual, the minimum is 1, and here it's the random effects regression, right? If we run the fixed effects regression, which is this one. So here we have fixed effects, the within regression. The correlation is not equal to 0. The probability of F is greater. As you can see here, it's statistically significant. And finally, we get also the different coefficients. The last step would be, so I have to store the results in order to compare between both. I haven't done so. And if you remember, it's important to do that in order to run the Houseman test after that, right? And finally, I will run the Houseman test for S3 and S2, what I wrote here, right? In order to see the Houseman test. And as you can see, it's statistically significant, which means that we have to use the fixed effects model, not the random effects model. Okay? An important 2 minor things before I listen to your questions. We said that in the fixed effects model, all time invariant variables have to be dropped, right? Here we can see that in the fixed effects regression, years of schooling, it didn't drop because it changes over time. But here the gender variable did not drop, which means 2 things. Either we have a data entry error, because in general gender do not change over time, or, which perhaps might not be very frequent in Egypt, is that an individual has changed his or her gender. But most probably it's more of a data entry error rather than a change in the gender. So that's why that's the kind of also things that we have to make sure when working with those data, to make sure that the results, they make sense, because in principle we should have expected that it's the case, right? And then, as I said, we run the Houseman test, and we have seen that for the Houseman test we get the fact that the random effects model is better than the fixed effects model is better than the random effects model, right? You will see in the do file a lot of comments and commands that help you work and play with the data. And to be familiar with all those techniques, perhaps you might have worked with panel techniques using macro data, but we have seen today how to work with them using micro data. And 2 final points before we answer different questions. It's important to bear in mind the fact that whenever you work on a do file, this do file has to be as clear as possible and as organized as possible. You will see the richness of the do file that you will receive. And the richer the do file, the easier for you and for your co-author if you're going to work later on the paper. That's on the one hand. On the other, never change the original data set. You have always to save your initial or your original data set in a safe space, and then you play with a copy of the data set, because in case you change something that is irreversible, you can go back to your original data set and work on it again, but never overwrite or save your changes in the original file of the data set. Okay? Hassan, you have a question?
Yes, Shahid, please. So I understand that you have to set your data as panel so that Stata can understand that you're going to be using panel data commands. But are we required to do some sort to sort the data before we ask Stata to treat it as panel, or we
Uh,
just keep it as is?
no, to declare that a data is a panel data, you don't need to sort. What you have to make sure, because in several cases, whenever you run this command xt set individual year, for instance, which is the individual variable and the year variable, you can get Stata can tell you that you have repeated values within panel, which means that for some individuals, you can observe more, the same year several times. For instance, Hassan 2006, Hassan 2006, and Hassan 2012. In this case, Stata cannot read the data as a panel because we have twice for Hassan 2006.
So I have to
That's
clean
why
it in this
you
case.
have to delete the duplicates whenever you get such a message, or you make sure that the data is panel. But in
Okay.
general, there is no need to sort the data. You sort the data only when you merge.
Okay, thank you.
Rashida?
Thank you. I have two questions, please.
Yes.
And the first one about Hsiao test, if it is obligatory or not. Hsiao test.
Hizao or Hosman?
Hsiao.
No, Hizao is for the dynamic panel, not for panel.
Not for okay, it's not obligatory for fixed and random panel
Random and fixed effects.
effects. No?
No,
Hsiao, the test of heterogeneity to verify if we have if we have a pooled or fixed or ran or panel data.
you mean the test of homogeneity?
Yes, homogeneity.
Well, I mean, you can run it, but I think in general the Hosman test is much more needed in the sense that it helps you determine which one is better. But for the Hizao test, you can use it if you wish, but it's not as necessary as the other one.
Okay, thank you. My second question is about how to run the do file.
Yes.
Because when we receive the do file, it named as you mentioned in the presentation, and we need to specify the direction of the do file. Can you share with us how we can change the direction of the do file to run it for our case?
You mean the directory of the file?
Work file, yes, for the do file.
Yes, so that's the command in general. It starts with cd. So for instance, what I will do, I will now you can't see my screen, right? Now you can see my screen.
Now, yes, yes.
So it's this
Now
command, cd. So cd, and then you write where the file is located. So for instance, in my case, it will be uh, something in these lines. It will be see users, Chahir, my
yes.
documents, and so on. right? And in this case, I will, if I run this, I will get the everything, the data, the do file, the log, everything in this folder. So it's with the command cd.
Okay, thank you.
Other questions?
Can I jump in with one more question, Shahir, please?
Yes.
Generally with panel data, sorry, not panel data, with pooled cross-sectional data, is it usually the case that fixed and random effects are also used? Aula, we don't generally use fixed and random with pooled cross-section.
No, put cross-section, it's about OLS regression. It has nothing to do with the panel.
Okay, okay.
So it's an OLS.
Mm, mm. We don't really, the different assumptions than the fixed and random effects. We don't use
Oh,
these.
definitely. I mean, as long as you are pooling data without observing the same individuals over time or without
Of course, yes.
observing the same countries over time, then it's not a panel data set.
Okay.
Evren?
I was just going to make sure that we didn't use the weights for our analysis, right? We
Here in this
used the,
regression, we didn't, but we should.
we should use them for the regression.
Yes. I mean, in some cases, results can really differ. In others, not that much. But to make it short, in general, it's better to use the weights, but it sometimes depends on the research question, because I remember I was working once with some firm level data, and I had not to use the weights because the variable itself was difficult to be weighted. So that's why I didn't use the weights. But the general answer would be yes, but it depends on some very specific cases, depending on your research question.
Okay, thank you. My second question is adjusted R-square irrelevant when we use panel data? Because I'm not sure our command reports adjusted R-square.
Here, actually, because you mean in the case where we're comparing different models, right?
Yeah.
Here, what we get in Stata is three R squared. The R squared within, so within a group, the R squared between groups, and the overall R squared. Stata does not calculate the adjusted R squared automatically. But as far as I remember, I have personally, in all my empirical work I do, whenever I report the R squared, it depends really on the journals, but in most of the cases, we report the within, the between, and the overall. I have never extracted the adjusted R squared, but I think it's possible, but I'm not sure. We might want to double check.
Oh, I get adjusted R-square from R, but it's always negative. And I read somewhere that I shouldn't use adjusted R-square for panel regressions, but I didn't understand why.
No, frankly, I don't have an answer for this, so I prefer to check before answering.
Okay, okay. Thanks so much.
Other questions or comments?
Mr. Shahir,
Yes.
can you please share with us maybe your email or email, I think, in case if we develop a question after revise again,
Yes, I mean, in these
then contact you.
in the slides that you're going to receive, you will have. Sorry. So in the slides that you're going to receive, you will have my email, and whenever you have any questions, don't hesitate.
Great, thank you.
Okay, so with that, given that it's 7 p.m. and it might be later in other countries, 8 p.m. in Cairo, 9 p.m. in Lebanon and Jordan, a bit earlier in Maghreb countries. So I think we can stop here now. It was a pleasure seeing you all online. Hope to see you soon in a conference or in a person an in-person workshop at ERF. Tomorrow you will continue with Rasha Ramadan, the last part of the online workshop. And as I said, at the end of the workshop, you will receive, if you attended all the sessions, you will receive the certificate, and you will receive a Google Drive link with 3 folders that include the data and the do files, the slides and the readings, in addition to our contacts that are written on the slides. Thank you again thank you once again. And again, I would like to thank Namis and our ERF colleagues for taking care of the logistics. Thank you and hope to see you soon.
Thanks,
Thank
Shahir.
you,
Thank
Mr.
you,
Ya'tik
Shahir.
Chahir, for
Thank you.
this brilliant
Thank
training.
you.
Thank you.
Thank you so much.